All right, everyone, today we're going to be talking about topic 3.4, the ideal gas law. And so we spent the last few lectures kind of thinking about the properties of solids as well as liquids in terms of IMFs and just their kind of physical properties. For this lecture, we're going to spend all of our time thinking about gases. And so for gases, there's a few important factors that we need to consider. One is temperature, or T. Next is pressure, or P. Volume, or V, and then the number of moles, which in this case we call N. All of these properties are important towards thinking about gases. So we'll start with pressure. Pressure is defined as the amount of force applied to an area. And generally we can calculate pressure as P, or pressure, is equal to the force over the area. Generally, we're not going to be solving this in AP Chem, but this is what pressure actually means. When we talk about atmospheric pressure, we're talking about the weight of air per unit area. Atmospheric pressure is something that's going to come up a lot in problems in AP Chem. You may also see this a lot on exams as well as practice problems, this idea of standard pressure. And so normal atmospheric pressure at sea level is referred to as standard atmospheric pressure. And so this is equal to either 1 atmosphere, or ATM. ATM equals atmosphere. It's also equal to 760 torr, or 760 millimeters of mercury. This is another measurement of pressure, or 101.325 kilopascals. Kilopascals being our SI unit. And just as a little bit more context, 1 Pascal is equal to 1 Newton per meter squared. We may have learned these units in physics, but this is what a Pascal directly translates to. Now, there's a few laws that govern how gases work. I typically like to call them the laws of old dead people because they were found so long ago. The first is Boyle's law, and so it says that the volume of a fixed quantity of gas at a constant temperature, so I'm going to say constant T, uppercase T, is inversely, meaning the opposite, proportional to pressure, or P. So in more equation format, what I'm basically saying here is V is proportional to 1 over P. Inverse, right? It is not proportional to P, it's proportional to 1 over P. Another really important equation that comes out of this is P1 times V1 is equal to P2 times V2. So if you have pressure and volume initially, whatever the start is. So if you're given a problem and they say you have a system with a particular pressure and volume, and then they tell you, pressure either will increase or decrease, then you can use this law to determine what the volume would be. And inversely, if we say pressure of 1 and volume of 1 goes to volume of 2, whatever that may be, then we can calculate pressure of 2, or P2, right? And so if you're looking at a problem that is looking at the change of pressure or volume, you can use this relationship to figure out what that would be. The next law that governs gases is Charles's law, and so this relates volume and temperature. So the first one that we talked about related volume and pressure. In this case, we're looking at volume and temperature, and this says the volume of a fixed amount of gas at a constant pressure is proportional to its absolute temperature. right? And so what we're saying here is that volume is proportional to temperature. And similarly, for Boyle's law, for Charles's law, we can have a similar equation, but this time, because we're proportional, we can say V1 over T1 is equal to V2 over T2. And so if you're given a volume of a gas at a particular temperature and you're trying to figure out the volume of a gas at a different temperature, or if you're given a volume of a gas and the temperature at the start, and then you're trying to figure out its new volume based on an increase of temperature, you can use this relationship right here to calculate that. The next law is Gay-Lussac's law, which relates pressure and temperature, or P and T. And so what this says is the pressure of a fixed amount of gas at a constant volume is proportional to the temperature. So P is proportional to T, and similarly to Charles's law, P1 over T1 is equal to P2 over T2. And so if you're given a gas at an initial pressure and temperature, you can figure out the gas at a new pressure given the temperature, or a new temperature given the pressure. And one important thing that comes out of this is that as kinetic energy increases, the force that gas particles strike the walls of a container increases. And this will increase the pressure. Right? This is what we mean when we are talking about an increase of pressure. The particles are moving around faster and they're hitting the walls of the container stronger. And so as temperature, right, as our temperature T is increasing, our pressure is increasing, and our kinetic energy is increasing. And these are all relationships that we need to keep in the back of our minds. The last of our gas laws that we're interested in is Avogadro's law. And this says this will relate the volume to the number of moles, or N. And this says the volume of a gas at constant temperature and pressure, or T and P, is proportional to the number of moles, or N, of gas. So V is proportional to N, and of course, just like Charles's law and Gay-Lussac's law, V1 over N1 is equal to V2 over N2. And so we can take all four of these gas laws and make this combined gas law that you see here on the right. P1 times V1 over N1 times T1 is equal to P2 over times V2 over N2 times T2. And so if you're given a gas at an initial state, and any three variables in the final state, we can calculate variable 4. Right, and so if you're given pressure, volume, number of moles, and temperature at the start of a reaction, say, or in one container, and then you change that container or react something in a certain way, if we're given pressure, volume, and temperature, I should be able to calculate the number of moles, and I can do that for every single variable in that final state. So if we're combining all of this together in the context of volume, we can see that volume is inversely proportional to pressure. So volume is proportional to 1 over P. That's Boyle's law. We've seen that volume is proportional to temperature. That is Charles's law. we see that volume is proportional to the number of moles. That's Avogadro's law. Right, and we also have the Gay-Lussac's law, which tells us that pressure is proportional to temperature as well. And so if we want to put this all together, right, this is basically telling us that volume is proportional to the number of moles from Avogadro's law, the temperature from Charles's law, and inversely proportional to the pressure from Boyle's law. And so if we want to turn this proportionality into an equation, we need to add a constant. And so what we can say is the pressure times the volume is equal to the number of moles times this proportionality constant, which I'm going to write out in red, R, times the temperature. And this right here is our ideal gas law. So anytime we have proportionality or some sort of relationship like this, and we want to turn it into an equation, we have to add a constant to it. And in the case of the ideal gas law, it's this constant R. And there are a few different units of R depending on what you're looking at, right? We have pressure, temperature, number of moles, and volume. We have a whole lot of different types of units that we can use for all of these. And so oftentimes you'll see R. So I'm going to do R equals. Its units can be liter atmosphere per mole times Kelvin. And so, right, this is our volume. Atmosphere would be our pressure. Moles would be our number of moles, or N. And Kelvin would be our temperature. And that numerical value that we get is 0.08206. Equally, we also have joules per mole times Kelvin. So joules is both our volume and pressure. Moles, of course, is number of moles, and Kelvin is our temperature. You can have calories per mole for Kelvin. Calorie, again, is both the volume and pressure used to calculate that. Number of moles is N, and Kelvin is our temperature. We can have meters cubed, where meters cubed is our volume. Pascal per mole times Kelvin is another unit for R. And finally, another common unit for R that we see is liter, which is our volume. Torr, which is our pressure, per mole, which is our number of moles, times Kelvin. So all of these numerical values here are given on the reference sheet for the AP exam, but it's useful to know when to use them, especially if you're given volume, pressure, number of moles, and temperature in a particular unit, how you can convert between all of those units and use R to solve the ideal gas law. And now, because of the ideal gas law, there are a few more important equations that we can learn and use in order to kind of study gases and understand how gases work. And first is Dalton's law of partial pressures. So what this says is if two gases mix together and don't react in a container, they act as if they're alone. And so they'll mix, but they won't necessarily react or interact with each other. And so as a result, the total pressure is equal to the sum of the pressures that each gas would exert on its own. Right, and so P total, right, P with a subscript T, is equal to P1 plus P2 plus P3, and so on. So as a result of Dalton's law of partial pressures, we can also relate this back to the mole fraction that we had learned in Unit 1. So because each gas in a mixture acts as if it's alone, we can relate the amount of the mixture to the partial pressures. And so if we're saying the partial pressure of whatever gas in our mixture, so P1 over the total amount of gas, Remember that P in the ideal gas law is equal to N1, right? The number of moles of our first gas times R times T. And so this will be over V, and that will be for P1. And we can do the same thing for P total. And so it'll be the total number of moles times R times T over V. R, T, and V are going to cancel for each of them, right? Because we're in one container. And so even though they act like they're alone, they're still in the same container. And so the temperature and the volume would be constant. And so if you're trying to figure out the partial pressure of one gas in a total, that will be equal to the proportion of the number of moles. And so you can also call the mole fraction chi or x. And so you have x is equal to moles of compound 1 over total number of moles, which is equal to N1 over NT. And so this is how you can relate a pressure fraction to a mole fraction. And so the end result here is if you're trying to figure out the pressure of one gas in a mixture, that would be equal to the number of moles of that gas over the total number of moles times the total pressure, otherwise known as the mole fraction chi or x times the total pressure. And so if you're ever asked to find the pressure of one gas in a mixture in a container where they're mixed together, then you would just take the mole fraction of your gas of interest, the number of moles of your gas of interest, divide it by the total number of moles, and multiply it by the total pressure of gas in that container, no matter how many gases there are. And so just looking at this practice problem right here, we're told that we have a gas mixture at 0 degrees Celsius, and so T is equal to 0 degrees Celsius, and 1 atmosphere. So our total pressure here would be 1 atmosphere, contains 0.01 moles of H2, and so N of H2 would equal 0.010 moles. We have 0.015 moles of O2, and so N of O2 is equal to 0.015 moles, and we have 0.025 moles of N2. N2 equals 0.025 moles. And so assuming ideal behavior, and so whenever we see the word ideal behavior, we always want to think ideal gas law. So PV is going to equal nRT under these conditions. So it's asking what is the partial pressure, or P, of H2. And so if we look back at the last slide, we know that P of any gas is equal to the mole fraction of our gas of interest times the total pressure. And so in this case, the pressure of H2 is going to equal the mole fraction, which in this case for H2 would be 0.010 moles times the total number of moles. And so 0.010 moles H2 plus 0.015 moles of O2 plus 0.025 moles of N2, right? Because we have to include all of them. And then we multiply that by our total pressure, which is 1 atmosphere. So we get the partial pressure of H2 is equal to 0.2. So our answer would be C. H2 comprises 20% of the total number of moles of gas. And so you can go throughout this entire calculation, or you can just simply look at our percentages here and find that that would be the answer. That's all for now. Thanks, guys.